Chill program. This is my control of autonomous project based on suspension system. In the suspension system, we will see modeling, analysis, control, PID control, root locus control, frequency control, state space control, digital control, and also we will see simulink of modeling and control. So, what is a suspension system? Suspension system is a vehicle which connects the wheels to the chassis and is designed to provide a smooth ride by absorbing bumps and irregularity on the road while also maintaining stability and handling. In the modeling, the physical setup of suspension system is from this image. Body mass, suspension mass, K1, K2, suspension constant, and also designing an automatic suspension system is an interesting and challenging control problem. When a suspension system is designed, a 1 by 4 model is used to simplify the problem to a 1D multiple spring damper system. A diagram of this system is shown below, and the equation and the transfer function of suspension system is this below. And the analysis of the suspension system, which is design requirement like a good bus suspension system should have satisfactory road holding ability while still providing comfort when riding over bumps and holes in the road. When the bus is experiencing any road disturbance, the bus body should not have large oscillation and the oscillation should dissipate quickly. Since the distance x1 minus w is very difficult to measure and the deformation of the ride of the tire x2 minus w is negligible, we will use the distance x1 minus x2 instead of x1 minus w. Is the output in our problem. Keep in mind that this is an approximation. The w is a road disturbance. In this problem, we will simulate by step input. This step could represent the bus coming out of the porthole. We want to design a feedback controller so that the output x1 minus x2 has an overshoot less than 5% and a settling time shorter than 5 seconds. For example, when the bus runs onto 10 cm step, the bus body will oscillate within the range of plus minus 5 mm and return to a smooth ride within 5 seconds. And the opponent step for the output is like this. This one we can see that oscillating and going through 0 in the x-axis. And the closed loop schematic of the suspension system is seen and the output is going to the input with the minus. And the control dynamic equation of the suspension system is u1 of s and g2 of s. Accordingly, x1 of s minus x2 upon u of s, x1 of s minus x2 of s upon w of s. The difference is u of s and w of s. After adding a PID controller, the closed loop response plot is this, which is a transient response. And the root locus with PID controller is this, which also left side. So we can say that this is a stable. After choosing the gain of PID controller, the output is it is transient as we see below above, and the root locus plot is this after adding a choosing the gain, which is a left side of the left plane, which is also stable, and adding a notch filter in the root locus which uh, which like this, and this is also be stable. And how to find a gain from the root locus, we will see in the next. We will see, and the plotting closure response is like this, which is also transient, but with zoom. And the frequency response in the MATLAB plot is like the, in the body plot and the magnitude in dB versus frequency graph and the phase versus frequency graph is like this, which is very one. After adding a lead control and the determine the constant from the equation below. Equation after solving the equation, the constant is like a is value is 0.031 and the t and at value following equation is 1 upon w under ai and at equal to under a by w. In the state feedback controller, full state feedback controller, we will see in the open loop plant A, B, C, K matrix, and the K matrix input is in the input. We will can see closed loop response equations x dot equal to this and y equal to cx, and this output is like this. And we can also see the digital controller design like this. y equation sampling time selection of the step response of the suspension system is like this. This is a negative linear, and the simulation of the closed response output is like the e of x. We can see in the plot that the overshoot is less than 5 millimeter and the response settled well within 5 seconds. Changing the axis allow allows a better view of suspension initial response, and the step output of this system amplitude versus time graph is the first of all goes to A and after decreasing. And my reference of this suspension control is from this.